All right, so we are now recording. So welcome everyone to the second session of the 2021 Developer Conference. I hope you've had a nice break since our fantastic session this morning. And in case you haven't noticed, the videos of this morning's session are now up as a playlist on the ArduPilot.org YouTube channel. So if you were asleep this morning and missed any of the talks, then you can go and watch them. There's a video of the entire session, or there's 4 separate videos of the 4 talks. So you can do it whichever way you prefer. So this evening, we have the pleasure of a talk from Samuel Tabor, who's coming all the way from Scotland and giving us a talk about ArduPilot Soaring. And there's been many exciting things happening in Soaring, so looking forward to it. Over to you, Samuel.
Great stuff. Thanks, Andrew. And hi, everyone. So yes, it's a bit of an update about the Soaring feature, of which I'm the maintainer currently. So a bit of a roadmap to this talk. So although the title is Soaring Update, I realize I haven't actually given a talk about this feature in the past. So to kick it off, there's a bit of an introduction, what it is, why would you want to do it, and a bit of the background about what thermal soaring is all about, and how we can make use of it with UAVs. Then there's a bit of a description about the current implementation in the code and some recent progress towards improving the existing features. And then the later part of the talk is around some of the new developments which are currently being tested and evaluated. And then finally some future ideas as well. So what is it? So it's a set of features to enable gliders to stay aloft for long periods of time without using batteries or other propulsion, or to do it automatically, ideally. And it's implemented as a library, AP Soaring, and as a flight mode, thermal flight mode. And the history of this technology goes back quite a long way before ArduPilot got involved with it. So it's been under research for quite a long period of time. This is about the mid-2000s by various research groups, including NASA and NRL. I got interested in it about 2013 and developed some of the features as a fork, which I had some fun flying, and then some other people did as well. But it wasn't until around 2017 when that work was picked up by a group under Microsoft, including Ian Gillard here, who's on the call, and they used it in their Frigate Bird project. The link to that is here on this slide. And as part of that project, they dusted it off and rebased it on the current ArduPilot master, and I went as far as getting it pull requested and brought in. Into master, which was a really great effort by them, as well as being a very interesting project in its own right. And once it was in master, that gave it a bit more visibility, and it got picked up for commercial use in around 2018 by a company, Kraus Aerospace, KH Aerospace, who are now using this commercially, and who I work for, as well as Tom works for them as well. So why would you want to use this set of technologies? Well, first of all, it's very interesting, at least for someone like me, a kind of nerdy engineer. So it really sits as the intersection of a lot of different interesting areas. So you've got the weather, you've got the performance of gliders and of aircraft. You've got a lot of scope for optimization in how the aircraft flies, and you've also got the inspiration of how nature handles it with various soaring birds. So, but as I mentioned, there's also commercial or industrial applications, and one that I've already mentioned is the Kraus Aerospace K1000 glider, which is a product which is really designed to take advantage of this technology of thermal soaring, as well as having a lot of other interesting features on the aircraft, including high efficiency solar panels and lots of other bells and whistles, like a high bandwidth data link and capable payloads. Now this aircraft, does have very good features for soaring. So it's got a 30-to-1 glide ratio, and it's got a very long ability to fly due to its high battery capacity and solar power, which means it's a great experimental platform for soaring, as well as being a very useful aircraft for our customers as well. And Craftsman Aerospace is an ArduPilot partner organization. But most importantly, it's a fun thing to experiment with. It doesn't need to be super complicated. I do the majority of the testing on a very simple Volantex foamy in my local flying field, and it's a nice way to get out and enjoy the good weather when it comes along, and enjoy flying your gliders. So a bit of a kind of background to what thermal soaring is, to kind of create a bit of a mental model for the subsequent slides. So it's a bit of a video here showing a kind of time lapse of what happens when thermal soaring conditions exist. So what you have is sunshine heats the air pretty much only right beside the ground. It doesn't heat the air that it passes through on the way down to the ground. And this creates a sort of blanket of warm air beside the ground. And as we know, warm air likes to rise, and eventually this air breaks through the cooler air above it and rises as a bubble or a column of warmer air. And we call this a thermal. And this continues up through the atmosphere until the expanding air, due to the falling pressure, cools down to the ambient temperature, at which point it stops rising. And in a lot of conditions on the way up, the water vapor that it carries from the surface will also condense out, forming these kind of classic cumulus clouds, fair weather cumulus. So here's another kind of visualization. So this is actually from a soaring simulator, Condor 2. And this is the advantage. It also has a sort of cheat mode where it will show you what the air is doing underneath these thermals. So you can see it's kind of sucking up warm air from a fairly wide area. And that's being pulled up into the sky and forming a kind of stream of warm air going up through the atmosphere. And also the wind has the effect of blowing these formations along with it. So if you were to take a slice through the atmosphere on a day like that, with these conditions, you would see something like this plot. This is actually a plot from a LiDAR measuring device pointing up into the atmosphere and measuring the vertical velocities of the air. And you would see that there's these isolated columns of red, which is rising air. And those are surrounded by areas of blue or sinking air. And overall, due to conservation of mass, this the whole thing balances out, so that there's as much air sinking as there is rising. So in order to exploit that, we need to make sure that we spend more time flying our glider in air that's rising rather than air that's falling. And because it's overall average, if we just fly in a straight line and don't make any changes, the effect on the glider will average out. We won't get any net benefit. So there's kind of three groups of techniques we can use to get a net benefit and stay up for longer. So the first one is effectively what's currently implemented in the code, and that's the technique of circling where the air is rising and flying in a straight line through where the air is sinking. And because you're spending then more time in the rising air, you get a net benefit. And there's three sort of components behind how that works currently that I'll talk about in the subsequent slides. However, there's also two other possible techniques which you can use to exploit these conditions, and which full-size, manned gliders do very, very effectively. And the first one, technique B here, is that you can adjust your airspeed so that you fly at a higher airspeed through air which is going down, which is sinking, and you slow down where the air is rising in the lift, where the thermals are. And even without stopping to circle, this will allow you to get a benefit. But you can also combine it with the circling, the thermaling flight path. You can combine those two techniques to get additional benefit. And this is a feature which is currently under development. The second half of my talk, I'll talk a bit more about the progress towards that. But there's also a third technique, which is kind of on our future roadmap, which is to actually actively navigate the aircraft, so that we're not just flying in a straight line through whatever thermals and sink we encounter, but instead we're picking our way from thermal to thermal and along lines of lift, so that by adjusting our horizontal flight plan, we can fly more through lift and less through sink. So the first existing feature of the code to talk a bit about is the variometer feature. And the purpose of the variometer is to try and back out what the air around the glider is doing using the measurements that the autopilot on the glider actually has at its disposal. This can be done by effectively measuring the climb rate of the glider and then adding on various corrections. So there's two principal corrections at present. So the first one is the natural sink rate of the glider in still air, the glide polar. So even if the air is not moving at all, the glider will descend at a rate which is related to the airspeed it's flying at. And that's related through the glide polar. And the second correction is an acceleration correction. And this arises because if you imagine doing a steep pull-up in still air, that would result in a climb rate. However, you'd also be decelerating. So we can add that in as a correction to improve the estimate. And this estimate can be used for various purposes, and there's various filters with different timescales for different types of decision making. So it can be used to decide when to stop and thermal. It can be used for actually adjusting the flight path within that thermal to better harness energy. And then it can be used for decision making as when to give up and leave a thermal. So the glide pool I've already mentioned, which is the sink rate of the glider as a function of its airspeed, even in still air. And in the implementation as present, there's 3 parameters which describe or parameterize this function. The first one is the K parameter, which is proportional to wing loading. And what this does is it doesn't affect the glide ratio, but it moves it to different airspeeds. And this is why full-size gliders have a good glide ratio, but it occurs at very high airspeed because they have a much higher wing loading than our small models do. The second one is the CD0 parameter, which is related to the zero lift drag. And this kind of comes in through the sort of aerodynamic cleanliness of the design. So if you imagine a very sleek and streamlined glider versus a kind of fairly rounded glider with lots of antennas and so on hanging off it, that would be the difference between the value of the CD0 parameter in your glide polar. And the predominant effect of this parameter is to adjust the rate of sink at higher airspeeds. So on the middle graph there, you can see it doesn't make too much difference, the different colored lines at the lower horizontal speeds. But the faster you go, the bigger a difference it makes. And the final parameter is the polar B parameter. And this is really related to the change of drag with lift. And it's mostly related to the aspect ratio of the glider, how skinny the wings are, as well as some other parameters of the design. And what this principally affects is the sink rate at the lower end of the airspeed spectrum. And its effect for our kind of typical range of parameters with model gliders doesn't have as big effect as the other 2 parameters do. So the kind of second component of the existing set of features I want to talk about is the management of the flight mode and the throttle. So currently, thermals can only be detected when the aircraft is gliding because the propulsive effect, the thrust from the motor, would disturb the estimate of what the air around the glider is doing. So the code will automatically suppress the throttle when appropriate to allow that detection to take place. However, there's kind of checks and balances on that. So as the glider descends, if it doesn't then find a thermal, the code will automatically allow the throttle to run again, and it'll climb back to a suitable altitude to start that search again. However, if it does find a thermal along the way, that's specified by the soar v-speed parameter. So if the air is estimated to be rising at a rate which will allow the glider to thermal at a vertical speed of soar v-speed or greater, then the code can automatically trigger into thermal flight mode. And there is an RC switch option to suppress that capability as well if you don't want it to do that. But it can do that automatically and start thermaling. And then it will revert to the previous flight mode under a number of conditions. So if the thermal climb rate drops below that specified value, or if it reaches the maximum specified altitude, it will go back to the flight mode you started in. And the 3 flight modes which are sort of supported as the kind of the baseline flight modes from which to switch are auto flight modes. So you can do a full auto mission, and it will stop and thermal if it finds something along the way. or you can fly more interactively in flyby RB mode or cruise mode. The third component of the existing feature set is the ability, once you have detected a thermal and stopped to circle in it, you can then, the code will adjust how the aircraft flies within that thermal to maximize the climb rate. And thermals, as we kind of saw in the previous videos, they're typically very irregular and turbulent. No two thermals are the same, but they do have some common features. So they will generally have an area of stronger lift within the thermal, typically somewhere in the middle, but there may be multiple areas of stronger lift. And the best strategy to maximize the climb rate of the glider once it's in a thermal is to circle around one of these cores of stronger lift. And in the code, we use a model-based strategy to do this, which requires that we have a model of what this thermal distribution of lift looks like. And we use a fairly common approximation, which is the Gaussian distribution of lift, which you can see here on the right, which has some of the right features. It has an area of stronger lift in the middle, which then has a smooth taper off towards the sides. Now, this is obviously not a physically accurate approximation of what a real thermal is doing, because it doesn't represent any of the turbulence or the non-regularity of real thermals. However, it is close enough to be useful, even though it's definitely not a fully correct model. So what we do with that model is we use the measurements from the variometer to feed into an EKF-like algorithm, which then estimates the 4 parameters of this model to effectively try to figure out where the center of the lift is, how strong it is, and how broad it is. So those are the 4 parameters of this model. And the algorithm is EKF-like because a lot of the complexities of EKF are kind of simplified out in this implementation, because we don't model any of the time dynamics of a thermal. So we don't try to update the states over time. We assume that it's fixed, even though in reality it's not. And we deal with any changes over time by just process noise in the estimator. And another major simplifying factor of this implementation is that we only have one measurement. On any time step, we only have a measurement of the local vertical velocity from the variometer. And that again simplifies the maths down quite a bit to keep that implementation quite simple. And it's interesting that even though we only have one measurement and only one time step, because we're taking multiple time steps at different positions, we're able to build up this model of the 4 parameter thermal over time. And as we saw before, the thermals drift with the wind. This is captured via a feed-forward term. So this estimator doesn't have to try to keep up with the wind drift. It already knows that it expects the thermal to drift with the wind. And then the estimated position of the central core of the thermal is then used as the target loiter point using the L1 controller. So this is a kind of result that you get from applying this. This is a plot of a climb in a thermal, and the kind of multicolored trace is the track of the aircraft colored by the vertical air velocity it estimates to be in that position at that particular time. And the blue line in the middle is the estimated location, central location of the thermal that it's trying to track. You can see at the bottom of this, when it first enters, there's quite a lot of variation in that estimate, and then it settles down a little bit as we get quite a constant climb rate in the lower third of the thermal. Then as we get higher, as we saw before, thermals are very irregular, so they change shape over time, and they don't fully obey the drifting of the wind that it expects. So in this example, we start to encounter areas of sink on the kind of the westerly side of the thermal. And at that point, the estimator tries to shift the estimate to better center in the lift and move the aircraft more to the east, to the kind of right rear of this plot. And as I mentioned, there's four parameters, and those are basically the states of this estimator, and they evolve over time, like in this example. Now, recent progress kind of within this set of features. There's been a large number of tweaks driven by the increased level of testing that we've had in actual environments. So that's led to a number of improvements to various aspects of how the variometer functions, and also various factors about how the EKF thermal centering operate to make it more robust and avoid some vulnerabilities that were found and improve the performance in a wider range of conditions. And the second broad category is kind of improved ease of use of this feature. So we now have thermal flight mode. Previously, we were doing thermaling in loiter flight mode, in a kind of special case of loiter. And that could be quite confusing for users, but also it limited, it meant that you didn't have loiter available for normal loiter type things. So separating that out gives us better flexibility and makes it a bit clearer to the user what's actually happening when the aircraft changes flight mode. So that kind of separation out has also enabled some other features to be added. So the first one is the separate parameter for the bank angle or the flight path radius to use when thermaling. So again, previously we were using the general loiter radius. And this was not very flexible in that you had to change that parameter if you wanted to do something other than thermaling, you'd have to switch it around. But also it meant that the default values weren't very suitable for thermaling. Whereas having a thermaling specific parameter allows us to have a more general default that will be more suitable for a wider category of users. So fly-by-wire B and cruise climb capability. So previously, the ability to automatically climb back to altitude and start gliding again to search for thermals again, that was only included in auto mode. It wasn't included in fly-by-wire B or cruise mode. And what would happen in fly-by-wire B and cruise mode would be that the aircraft would descend to the minimum altitude, and then it would go into RTL mode, and that wasn't very satisfactory for users, especially people flying long distance with FPV. So having this ability to climb back to altitude and start another thermal search is much better for those users. We now have more RC switch options. So the user, by toggling the switch, can invoke different actions. So if they're already thermaling, it can tell the aircraft to leave the thermal. And we also have a kind of a middle option on the switch. So we have a switch option to completely disable soaring. We have a switch option to enable all the features. Then we have an intermediate position which enables gliding and enables the variometer, but it disables automatically changing flight mode. So the user can still trigger thermal flight mode via their mode switch, but the code won't do it automatically if they don't want it to. We've done a number of documentation improvements to make the setup process easier for users. And we've also developed a glide polar calculation spreadsheet tool to help them estimate these three parameters I mentioned before, based upon the measurements of their glider and the results of glide testing in still air. So that kind of sums up the current state of the code and the recent progress made on those existing features. So that's 20 minutes in. So I'll pause for any questions at this point before we go on to kind of the areas of active development.
So I'm curious, Samuel, about the radius. I mean, you're trying to circle the core of a thermal. Yep. Clearly, there's more lift towards the center of the core, so that would tend to push you towards a narrow radius circle to get more of that lift. But then you'd be at a high bank angle, so that's less efficient flying. Is there a sort of a theoretical way to balance that, to optimize that radius, and is that something that is dependent on the flight conditions?
There is, yeah. So so you're right. So there's a trade-off there between getting in closer to the core of the thermal in the stronger lift, but turning tighter and having a higher drag effectively and a higher sink rate relative to the air. And for any set of aircraft characteristics and set of thermal characteristics, there is an optimum thermal radius and bank angle that gives you the best climb rate. However, to come up with that optimum, you need to have a good estimate of the distribution of lift within the thermal, and that really comes down to how strong it is and how broad it is. Now, fortunately, in our implementation, we actually estimate both of those parameters using the EKF. So it would be possible to use that information to dynamically update the flight path radius to maximize the climb rate. So that might be a future area of possible improvement. There is one caveat to that, which is kind of subtle, but even though we have these four parameters that characterize the thermal, when we're in a constant steady state turn around the core of the thermal, two of those parameters become confounded and they become difficult to estimate independently. And those two things are the strength and the radius. And you can kind of understand this by thinking about if you're in a very strong thermal, but it's very narrow, versus a weaker thermal, but it's very broad. At some radius, the updraft strength will be the same. And if you're thermaling at that radius, you can't tell whether you're in a strong narrow thermal or a slightly weaker broader thermal. So those two parameters are quite difficult to estimate. And that's why up till now, we haven't tried to use that information to dynamically update the bank angle, because they tend to become slightly confounded.
How much would you need to weave in the circle if you had a sort of a rippled circle,
Right.
like a sewing pattern type circle, would that give you enough observability?
It would, yeah. And the nice thing about the EKF implementation is that it does have a covariance matrix. So even though it can't accurately estimate these two parameters, what it knows that it can't do this from the observability calculations. So it knows that these two parameters are confounded. So the covariance term on those two states becomes very high over time, because it knows it can't independently estimate them. So as soon as you actually go out of a circular flight path, it will very quickly use that high covariance term to update the estimates to make them more accurate. So what we actually need to exploit that is a heuristic that says that every now and again, rather than fly a perfect circle, fly more of an oval to actually get that other information from different radii.
Could you even fly like a bow tie pattern and actually go right through the middle? And that would give you great lift in the middle at the expense of some steeper bank angles. But that would also give you great observability, I would have thought, if you flew a bow tie.
Yeah, absolutely. And there's various kind of ways of handling this in the literature. So various different groups have tried just perturbing the flight path radius a little bit and see if that improves things or makes things worse. I think that there's some issues with that just because the thermals are naturally very variable. So you don't really know if you how long do you need to sample over to actually estimate that accurately. Whereas the EKF, because it has a better handling of noise, it kind of has a more natural way of handling that. Possible future
Thanks very much. So probably enough questions from me. Anyone else?
Yeah, I mean, I should just point out that's that's exactly what we tried to address with our Bomdisaur algorithm at Microsoft. So so it tries to balance that exploration and exploitation, to explore the thermal and learn the parameters of the EKF, and then once it's got a good lock, it tries to exploit them, and it's choosing actions optimally. So it's not necessarily just circling. It could be doing something like a bow tie or whatever it decides is the best way to do that exploration and exploitation, in the most optimal manner. So
yeah, it'd be really nice to get some of those features in.
Right. Yeah.
Can I ask how tight you're turning? What sort of bank angles you're using? Because like I used to fly thermal soaring, like full size thermal soaring, and it was actually one of the first things that got me interested in using autopilots. So so what sort of bank angles are you holding in the turn, and have you are you working on an optimal bank angle versus lift type equation to choose that?
Yeah, great question. So yeah, I've also kind of in the last couple of years got into full size soaring as well. And with full size soaring, they really turn tight, especially in Scotland, I think, because the thermals are quite weak and narrow typically. But 45 degrees is kind of standard for a full size glider. For models, it's kind of an area or UAVs, it's kind of an area for investigation. So I've found that typically in my testing, a little bit wider works better. So maybe 30 degrees of bank or so works quite well. But that's not really based upon any kind of optimality. That's really just based on experience. So right now we leave it up to the user what they choose. But it would be a great feature to have that calculated dynamically.
Yeah, because even I also fly. I haven't for a while, but model like high performance F3B sort of F3F sort of thermal soarers, and they crank it like you notice when you can core a thermal well, and you, especially low down, once you get higher up where I assume you guys are working, you know, perhaps the thermals are so large compared to the aircraft, you know, it's you know, the bank angle is much less important than a full-sized aircraft, for example.
Yeah, that's definitely a factor. So yeah, so the kind of scale of the typical lift structures changes based on how high up you are. So yeah, when you're low down, like the F3B guys and so on, they're kind of turning in tiny little bubbles of lift and little eddies. So they really need to turn tight to exploit them, because they are typically down quite low. And as you get higher up, those structures become more large scale. The kind of areas of lift come together to form larger columns, and that's where the full scale gliders fly, is in the kind of upper half of the boundary layer. For that reason, the thermals are stronger and wider. And that's where, you know, when we're doing commercial operations, that's where we'll typically be operating as well. So the lift structures are wider there, so we can afford to turn a bit looser. But I think that probably doing that dynamically would be a fairly major effort. So right now we kind of leave it up to the user to specify. But fortunately, there's a kind of, by specifying it using a bank angle rather than a turn radius, we kind of we reduce the variability a little bit, because lighter aircraft flying at lower flight speeds will typically want to turn a tighter radius, and parameterizing that as a bank angle, it kind of comes naturally. So while like a full-scale glider would be turning, you know, maybe a 150-meter radius or something, it might do so at the same bank angle that a small model would turn at a 10 or 15-meter radius.
The prediction, your Gaussian lift model, that would sort of somewhat, that should be sort of spitting out like an idea of the radius of the lift, and from that an indication of what some idea of what at least a suboptimal radius would be.
That's right.
So there like a very least a sort of a maximum radius that you should be turning. So there might be an opportunity at least there to sort of say, look, you should be, we perhaps should be increasing our bank angle here, or something like that.
That's right. Yeah. So yeah, I think we'd probably, to do something like that, we need what Tridge mentioned and what Ian did previously, which is to perturb the flight path to gather that additional information to improve the confidence in that estimate. That would definitely be a nice thing to have in the feature set.
No, awesome, love it.
Hi, Sam.
Hey.
So you mentioned that you're suppressing throttle specifically to be able to detect the thermals. What would you need in addition to be able to remove that constraint? Would you need to make any additional measurements so that we might be able to use motor gliders to push through regions of like high sync as well?
Yep. So next slide, please. So right. So this is an area for kind of active development. So shall I continue with this, or are there any other kind of burning questions before I continue on? Okay. So so right now, to sum up, we only detect thermals when there is propulsion suppressed, because we don't have an adequate correction for what effects the propulsion introduces. And this actually can cause a problem in some conditions. So if we have a situation where we want to use soaring, we want to use thermaling, but the conditions aren't quite strong enough to remain airborne purely using thermaling, we end up in this kind of gliding descent, and then followed by a climb, and then a gliding descent. So we end up with this kind of saw-toothed climb glide sequence, and this can be a bit of a problem. So for kind of a few different types of vehicles. So if your vehicle has quite a low climb rate relative to its descent rate, this can mean that you actually spend a substantial proportion of the time climbing back up before you start another glide, and there's a good chance that you'll be climbing straight through the thermal that you'd like to be harnessing, so you miss it. And then secondly, for vehicles which have very highly optimized propulsion systems, so the Crescent Down Aerospace K1000 is definitely in this category. We spend a long time designing propellers and optimizing propulsion systems to get a very low cruising power. So the efficiency is optimized at the one cruising condition, which is a steady state, constant altitude condition. And the kind of climb glide cycle is overall less efficient. This actually shows up in some of the data from our 12-hour flight, which you can see here. So there's a couple of features to point out in this. So what we have is a few different kind of phases within this flight. So we have the takeoff phase right at the start, followed by a steady state cruising phase for the first sort of 4 hours, really. And then after the first roughly 4 hours, we start to see thermal activity. And we want to start utilizing that using soaring. However, the thermal activity isn't quite strong enough, as I mentioned, to have a sustaining flight all the time. With those times where we're descending and hitting the minimum altitude and motoring back up. And due to the reduced efficiency of the propulsion system when climbing, this actually results in an increase in the average power for those time periods. So even though we're spending some of the time thermaling, the reduction in propulsive efficiency is still overcoming that, and our average power consumption is higher in those points. So that happens at the start of the day, or kind of when the thermals are just beginning, and it happens at one point in the middle of the day when the thermals just happen to die off over our area. Then it happens again towards the end of the day when the thermals start to taper off, and all three of those occurrences are accompanied by an increase in the average power consumption. The yellow is the solar generation for this vehicle, so not relevant to this discussion. So that's a problem. So we'd really like to get the efficiency back to, or the average power consumption back to no greater than the average. It should really be better than average if we're doing some thermaling. It shouldn't be higher than average. And also for aircraft flying missions which have restricted altitude profiles, reducing this climb glide cycle makes it easier to interface with ATC and to remain within your altitude permits. So to kind of reiterate exactly what's happening there, so this is a kind of a simulated example of that same mission profile. So takeoff, long period of cruise, constant power, and then period of this sawtooth pattern, which has a higher average power due to the greater power during climb, and then periods of thermaling interspersed with periods of higher power due to climb glide. Now, what we'd really like to do is to get to something like this, where we cruise in steady state, and then we have soaring enabled, but even if there's no thermals, we want to have the power no higher than the cruising power. And then we want to be able to thermal and not use any propulsive power. And if the thermals die off, we want to go back to a cruising power, but no more than that. And then at the end of the day, we want to go straight back to cruising power and not have any higher power areas. So to do that, we want to detect the thermals from the steady state cruise condition. And this requires us to add on a correction to the variometer estimate. So we had this same equation before, apart from now we've got this propulsive term. And actually we have already all the information that we need to add this on. So the text already knows from its parameters how much specific power it's putting into the propulsive system by looking at the maximum climb rate, the maximum throttle, and the trim values. So we can actually already use this to correct the estimate, and this then allows us to be able to detect thermals straight from the cruise condition, which it kind of has pros and cons. So right now it's implemented as if for testing, it's not yet PR'd as a kind of separate soaring mode. If you set soar enable to 2 rather than 1, you get this behavior. So the pros are that you reduce the user intervention. So for these very long missions, obviously this isn't relevant to most users, but if you're doing very long missions, you don't have to make a decision about when to enable soaring. You can actually have it enabled all the time because there's no trade-off with this increased power consumption. You improve the efficiency while you're waiting for thermals to fill in. You're able to detect more of the thermals because you're not spending some time climbing through them. You don't have this, makes it easier to interface with ATC due to the reduced altitude variation. And it's less intrusive to your kind of general mission profile. If you're trying to fly a payload and you don't want to be doing this climb glide, then that's better as well. And it's also potentially more applicable to kind of general usage of aircraft. If people are flying, if people are out for a kind of FPV joyride, they don't necessarily want to have this kind of fairly intrusive climb glide cycle that comes about through soaring. Maybe they just want to cruise at a constant altitude, but they want to be able to opportunistically take advantages of thermals if they happen to run into one. So there are a couple of cons, however. So there's once this is enabled, the accuracy of the text parameters then feeds into the ability and the accuracy of thermal detections. So if you're flying in extremely marginal conditions where you really want to tell the difference between a thermal which just allows you to climb at your specified rate and one which doesn't quite, then errors in these parameters will reduce that accuracy. However, it doesn't affect the accuracy of actually centering a thermal, because once we start thermaling, the throttle is then suppressed again, so the accuracy estimate goes back to whatever it was, so that error will be removed. And that those kind of parameter settings just introduce a little bit more scope for user error. But overall, for people who are flying vehicles which are well set up, I think the pros vastly outweigh the cons. So any questions on that aspect before I go on to the kind of next feature under development? 40 minutes in now to the talk. Okay. So the next kind of aspect under development is what I mentioned previously with regards to the kind of second technique B, which you can use to exploit the lifting thermals. And this can be used with the circling flight path or as a second separate method. But essentially, what this relies on is changing the airspeed dynamically to maximize the performance of the aircraft given what the air around it is doing. So whenever we're gliding from a given altitude, what we really want to do is we want to maximize how far we glide, because that will give us the two things. It will give us the widest area possible for detecting thermals. So the further we glide, the more chances that we actually intersect a thermal and start to exploit it. But secondly, we also probably want to make some kind of progress towards whatever objective we have in our mission. Now, if the air is still, when we have the best glide speed for the aircraft, and that is essentially the airspeed which gives you this furthest distance. And this plot shows the glide pull of the aircraft. So it's the vertical speed of the aircraft as a function of its horizontal speed. And this way of drawing it is a kind of graphical method of estimating the best speed to fly at to get the furthest distance. And what you essentially do is you draw a line from the origin of the plot, which just intersects tangent to the glide polar. And in this case, that occurs at effectively the minimum airspeed of 16 meters per second. So 16 meters per second is the airspeed you should fly at to maximize your glide ratio, the distance you can travel for a given height. However, usually in between thermals, we don't have still air. Usually we have some sink, which is balancing out the lifting area in the thermals. And usually we have headwinds or tailwinds, which affect this calculation. So this plot is the same as before, apart from it shows what is the effect of having an additional vertical speed component due to air movement, WZ, and an additional horizontal air movement, WX, due to wind, headwind. And you can see that if we draw the same diagram, we now have a much shorter distance that we can travel due to the effect of these adverse wind conditions. And that then means that the optimum airspeed to fly at is now different. And there's a theory which tells us what's the new optimal speed. And we can again use the same graphical construction technique where we, for this example of 1 meters per second of sink, we move the glide polar down to add that 1 meter per second onto the original vertical speed. And then we repeat that tangent process and we come up with a new airspeed, which as we expect is higher. So if we're flying in sync, we expect to want to fly faster to get through it. And the new airspeed has now gone from 16 meters per second all the way up to 21 meters per second, just with 1 meter per second of sink, which isn't actually a huge amount. So it's quite a big change. But usually, to kind of simplify the diagrams, rather than redraw the drag polar, the glide polar, usually we just draw this intercept to a different point on the graph. So rather than drawing the intercept line through the 0, point, we draw it through the vertical point corresponding to the level of sink. We get the same result. That 21 meters per second is the best speed to fly at. And this also works for headwinds as well. So in that case, we offset the starting point of the tangent by the sink speed and the headwind speed. And this example shows that if we're flying in 1 meter per second of sink and 5 meters per second of headwind, now we need to fly at 23 meters per second to maximize our distance traveled. So we're already, we're creeping up and up as we add more and more effects. What if we know, however, that we actually are expecting to find a thermal up ahead of us that will give us a certain climb rate that we expect? Well, fortunately, this theory, amazingly, also works for this situation. And what we do is we add that effect, forgetting about headwind for now, we add the expected climb rate on as an additional vertical offset to the starting point of the tangent. And what this tells us is that if we're expecting to find lift ahead, that means we should fly faster. And what this is now solving for is, rather than the distance that you can travel for a given height, it's actually optimizing now the average speed cross-country from thermal to thermal, which is quite amazing that the same technique works for both scenarios. And it's quite nice that to combine the effects of sink and an expected thermal, you just add those two numbers together as the vertical offset. And this also works fine for headwinds as well. You just add that offset to the graph as well and draw a new intercept. And in this example, we've got the three sort of combined effects, which, if we're flying in 1 meter per second of sink, we've got a 5 meter per second headwind, and we're expecting a 2 meter per second thermal climb at some point in the future. This is now telling us that rather than fly at our 16 meter per second still air best glide speed, we should now fly up at nearly 31 meters per second. So a massive change of optimum airspeed in a fairly realistic set of conditions. Now, typically full-size manned gliders, because they fly at a higher airspeed, so they're typically flying somewhere between maybe 60 and 90 knots for a cross-country flight. The effect of a 10 to 20 knot headwind is actually significant, but it doesn't change this too much, and they can afford to add that on later as a kind of correction. So what they typically do is, because lift and sink, lift or sink in the current between the thermals has the same effect as the expected climb rate in the next thermal, they take those two parameters, lump them together, and they do effectively a 1D lookup for what the best speed to fly is. And they very cleverly do this by adding an additional ring to their variometer, which allows them to adjust their expected climb rate and read off what the best speed to fly is. However, for us flying models or UAVs, typically at lower flight speeds, so it might be as low as 20 knots for a foamy, so that the effect of a 10 to 20 knot headwind is going to be catastrophic. We really want to capture this this effect of wind in our calculation. So we need to retain the more complex relationship. And the kind of graphical solution that I presented before, that can also be written out as an optimization problem. And this is what we have implemented, and this is what is currently being tested to maximize to get the best speed to fly. So there's this rather imposing looking equation, but don't worry, I've solved it for you. And this has really got a few inputs. So it's got V thermal, which is the expected climb rate in the next thermal, and that comes straight from the soar V speed parameter. We've got the wind component along your course over ground, which comes from the AHRS. And then we've got the local wind between the thermals, the vertical wind component, lift or sink, which comes from the variometer estimate. And I said I solved it, but actually there is no solution to this, so it has to be solved numerically. And this is done with a Newton method solver. And what we do here is we just run. So this is a shape of the solution, I should say. So for any So this is the shape of what the solution looks like. So it's a fairly well-behaved solution, which is why Newton method works quite well. And typically Newton method will converge in 3 or 4 iterations, will get you very close to the final answer. However, we'd rather not do, a kind of multiple iterations per loop inside the Soaring controller. So rather than do that, we actually just generate a new solution on every call through the Soaring controller. It just does 1 iteration of Newton, and it starts from the previous estimate from the previous loop using the new inputs. So the inputs change, but they actually change not too quickly compared to the loop rate, because these are all filtered estimates. And that means that the previous solution is actually a fairly good approximation to the solution to the current set of inputs. And we just do 1 single updated iteration, and then we use that as the speed to fly. Now, although this method never actually converges, because the inputs are also changing on every time step, it actually gives better accuracy than if we were to freeze the inputs and do multiple loops over multiple iterations over multiple loops, because we allow the inputs to change continuously. So it never converges, but it gives good accuracy. And the initial flight data from this implementation has been fairly promising. So in the final implementation, there'll be more smoothing associated with this, but you can already see that there's a correlation between the red in the top plot, which is the local sync rate, and the calculated speed to fly in the bottom plot. Plotting it out like this makes it a bit easier to see. So for any measured local sync rate on the x-axis, we're coming up with a best speed to fly on the y-axis. And this has been binned according to what the horizontal wind speed is. So you can also see that for any given sync rate, a greater wind component, a greater headwind component, which is more negative, results in a higher airspeed as expected. Now there are a few oddities to this plot. So there's a bit of a gap here, in that no measured sync rate will result in an airspeed which is between 10 and 11 meters per second. And this turns out to be due to a missing term in one of the special cases we need to implement for when to fly at the minimum airspeed. So that gap will be fixed. And this appears to have resulted in some spurious solutions, which is probably due to this discontinuity and the Newton method not quite converging, or not converging adequately on a single iteration. So I expect in future flight testing, once this missing term is input, those spurious solutions should go away. If not, we'll deal with them some other way. In terms of how this is going to be set up, so there's going to be a new parameter, soar cruise airspeed, and for that one, 0 will be the kind of default, which will be disabled, which will mean it uses the trim airspeed in between thermals. Greater than 1 will mean that you just fly a fixed specified airspeed, so it won't do this calculation, but it'll give you the ability to just say, I want you to fly at 15 meters per second as a separate setting from trim airspeed. And then finally, -1 will be automatic, meaning do this calculation and work out what you think is the optimum speed to fly at. So some kind of big pros from this will be improved performance. So I really expect that this will improve a lot the kind of average sync rate in between thermals and allow us to really maximize how far we can travel and generally improve the performance of the aircraft when soaring a lot. Secondly, there's going to be less user intervention. So right now, when running these long missions on the K1000, but also more generally, the user, if they're flying through a large area of sync, they might interactively set up a higher airspeed to get through that. And this will now automatically be taken care of. Potential cons, so because this relies on a number of different estimates, for example, the polar parameters feed into it and various other things, there's a little bit of additional scope for user error in setting those up. This will be more of an advanced feature to enable once the aircraft is flying correctly in other ways with soaring. And then secondly, there are some potential new couplings between errors in the glide polar and how the speed to fly theory operates. So that's still to be worked out, whether there is any instability there, and if so, how we'll deal with it. But I don't expect it to be a big problem. So to wrap up, I think it's a really big potential benefit from this method. It does need a bit more refinement. You can see here one plot from a flight of the K1000, where this is quite nice because it shows the amount of lift and sink we're measuring as we fly between thermals. And here you can definitely see that there's areas where we're flying through neutral air or slightly rising air, and then areas where we're flying through big sink. So this adaptive airspeed will really help out with that. So that's kind of the speed to fly. So to wrap up, so there's only 5 minutes left, so I'll wrap up fairly quickly. So with soaring in general, as we've already discussed with some other possible improvements, there's massive potential for future optimizations and future features to improve the performance of this kind of aircraft. But also, I think that the current features would really benefit from a wider community of users and testing. And towards that, there's a few things I've been looking at. So improved documentation I've already mentioned, and I'll continue to work on that to make it easier for people to get into it. But also there's the potential for maybe opening up to operation of aircraft which don't have an airspeed sensor, which is a current stipulation is that the aircraft must have an airspeed sensor. It may be possible to relax that, obviously with some performance decrement, but it might still be useful to get those users enabled. So more challenging simulated test cases would be nice. We have a fairly simplistic test case in the SITL simulator, which is run as part of the auto test suite. And then we have some more complex interactive simulators. However, having some more realistic automated test cases would be really great to validate some of this more advanced capability. Then the last one I have here is a lot of these features are quite difficult to reliably benchmark outside of simulation. And that's because the conditions we're trying to exploit are fundamentally stochastic and non-repeatable. So if you're trying to fly the same aircraft twice with different versions of the code or different features enabled, you can't expect to get a reliable idea, except in a very kind of probabilistic sense, about whether the change made an improvement. One way of getting around that is to have multiple aircraft flying in the same weather conditions. And this is something that I think is going to be very big this year. So I've actually got set up with multiple almost identical aircraft, which I'm going to use to do back-to-back testing of different variations. And then finally, to kind of leave you with this very quickly. So this is the kind of future potential for the third technique I mentioned, which is doing more intelligent route planning across between different thermals. And this, is really a kind of future effort, and it may be something which has to run on a companion computer or a more complex system. But the idea with this is that we have a bunch of information already about where we might expect to find better lift conditions. And that can come from knowledge of the terrain, so different terrain features are more likely to generate lift and thermals, as well as different weather conditions, for example, the wind direction and the sun angle. So we might use that to work out a kind of a priori map of where we expect to find thermals. However, even better might be if we do have multiple aircraft for certain missions. This is more probably for the commercial, the industrial application. But if there are multiple aircraft flying in a swarm, then they can start to share information. So if one of them happens to encounter a thermal, it can then communicate that to the other aircraft. They can use that within their route planning to do a better job of preferentially flying through better conditions. So that's the end of my talk. So so we're quite close to the top of the hour. So if there's any questions, let's have them quickly.
Well, we don't need to rush it. We can go a few minutes over if we need to. It's a fascinating talk. I really, really appreciate it, Samuel. I'm very interested in the non-airspeed operation. And one thing that might be worth looking at is we could use the replay facility in the EKF to allow us to rerun flight logs without the airspeed sensor and look at the estimated airspeed and estimated wind so that means any of your flights you do with an airspeed sensor, you could then run a script over it to see how well it would have done, at least on the airspeed and the wind estimate, which is the key thing, I guess, if you hadn't had an airspeed sensor. That might allow you to start providing some advice on how well it might perform and make that decision as to whether it's recommended. That should be, we'd need a small tweak to replay to allow us to disable the airspeed input, but that should be quite easy.
Yeah, that'd be really interesting. And maybe as a kind of extension to that, we could also bring in some of the soaring features into the replay. So the soaring estimator, I have a kind of a local replay capability using my MATLAB tools. But if we could do that same technique and assess how much impact there would be on those bits of code, that would also be be quite useful in making that decision.
Yeah, definitely worth looking at. So questions from others?
Yeah, really great talk. Thanks, Sam. What simulators have you integrated now with this?
Yeah, so I think back when Frigatebird was running, you guys did a lot of work with Silent Wings, if I remember. So there's that one which hasn't really received as much use as it should. But the one which I'm working more with now is called Condor 2.
Right.
And that one's quite interesting because I think it's a bit more actively developed than Silent Wings is. But also it's got a really great community around it. So at my kind of local full-size soaring club, they do weekly sessions where they will go and fly in Condor. And even amongst those very experienced soaring pilots, it's got a great reputation for the accuracy of the weather conditions. I think they described it as frighteningly accurate, frighteningly realistic.
Yeah.
So that's a really great kind of recommendation from that community about how useful that might be for actually tuning up some of these features.
But you haven't got that working with Shuttle yet. That's future work.
So it is working. So it does need a bit more work. But yeah, that for future, I think that's going to be quite important.
Yeah, great. Is there any plans to maybe do some parameter learning as well? Like the glide. I think the glide polar. Maybe for some users that's something they're just not really going to bother with, or maybe they change the weight of they put some ballast on and forget to change it or something like that. Like maybe being able to learn that glide polar would be quite a useful addition, perhaps. Is that something?
That's right. So yeah, so that's actually implemented, and it's had some testing already. I haven't included it in the talk just due to time, but that is implemented, and it does work actually. I've used that on my gliders. However, that again does need a bit more testing, and it doesn't completely remove the possibility of error. So, but to accurately estimate the glide polar, you need to be flying in still air conditions. That's one thing. Right. And you also need to be able to hold airspeed fairly accurately as well. So it's kind of an open question whether it's better just to estimate from glide testing, or whether to use this online learning. But it does exist, so I'll point you at it for your testing as well.
All right. Mm-hmm. Thank you.
All right. So if that's the end of the questions, then thank you very much to Samuel for a fantastic talk, really enjoyable. And I greatly appreciate the detail in the slides, and looking forward to seeing some flying in our local flying field with Ian. So up next, I'll just switch over the recording, ready for starting recording the